Hello everyone, thank you for coming to my presentation. I'm Sanjeev Venkateshwaran, a PhD student at the Department of Chemical Engineering at Texas A&M University, and I'll be presenting on model-based fault detection and isolation in nonlinear systems. So here's the outline of the talk. I'll start with the background and motivation, where I'll define what faults are, how they occur, and their consequences. Following this, the objective of this talk will be stated, and then I'll move on to discuss residual generator-based fault detection. And these ideas will then be extended to fault isolation. And finally, the method will be applied to a CSTR example. So what is a fault? A fault is an unexpected large deviation in process variables from usual conditions. These could arise due to numerous factors including mechanical failures, power failures, and also human errors. The consequences of faults can range from off-spec production to explosions, resulting in injuries and also fatalities. In the next slide, we'll look at a couple of such examples where the consequences have been disastrous. So one such disastrous consequence of faults was in the T2 laboratories in Florida, where the reactor exploded due to cooling system failure, and this resulted in runaway. So in this incident, 4 people were killed and 32 people were injured. And in another incident in Louisiana, a reboiler exploded due to liquid propane leakage, and this resulted in 2 deaths and about 114 injuries. So the objective is to develop a model-based scheme to detect and isolate faults in nonlinear processes that would enable corrective action to be taken so that you can ensure safe operation even after the faults have been detected and isolated. So essentially, say we have a process, we'd like to generate signals that would tell the engineers whether it is operating normally or whether there's a fault present. And if there's a fault present, we'd also like to know the exact type of the fault amongst a possible set of faults. And this latter part is what we call fault isolation. So now I'd like to formally state the fault detection problem. Uh, so, and in particular, we'll be looking at disturbance decoupled fault detection. So consider the system shown where x an n-dimensional vector represents the states, y a p-dimensional vector represents the outputs, w a d-dimensional vector represents the uncertainties or disturbances present in the system. These basically are the normal process variability that you would have in any system. And like in chemical engineering, a good example of this is chemical reactions because they are usually uncertain since they are empirical rate expressions. And F represents the fault. So the goal here is to detect F in the presence of those uncertainties using the measurements Y. In this study, the focus will be on observer-based fault detection. So consider a process that has its own share of faults and disturbances. This process also has an output Y that basically represent the measurements. So using this Y, we need to make conclusions on whether the process is faulty or not. And to do this, we have another system called an observer that takes the measurements from the process as input, and it in turn spits out a scalar output called the residual. We hope that this residual has properties that would facilitate fault detection. And what these properties are and how they look will be covered in the next slide. But before moving on to that, it's important to note that in fault detection literature, observers used are mainly known as residual generators, and that is the terminology that we'll employ in the rest of the slides. And in particular, in this study, we are looking for linear residual generators to help us detect and isolate faults in nonlinear systems. The reason we are looking for linear residual generators is because, as we'll see later, they enable eigenvalue assignment and hence the stability analysis or the convergence analysis of the observer aerodynamics is much more easier. The residual has two main properties. One is that it should asymptotically decay to zero in the absence of faults, and two, it should converge to a non-zero value in the presence of faults. These two properties can be broken down into three other conditions that would guide us in designing the residual generator. The first one is what we call the functional observer condition, and this says that the residual should asymptotically decay to zero in the absence of disturbances or faults. The second one is called the disturbance decoupling condition, and here we want the residual to be unaffected by any disturbances. So this will preclude any false alarms. And the third one is, and arguably the most important one, is the fault detectability condition, where you want the residual to somehow be affected by the fault. So this will ensure that you can see when a fault occurs just by analyzing the residual. In the following slides, mathematical formulations of the three conditions will be provided, and later necessary and sufficient conditions for the residual generator to satisfy them will also be derived. In this slide, we present the functional observer condition. So for the residual generator given by 2, to satisfy the functional observer condition for the process given by 1, there must exist a differentiable map T of x from Rn to Rs such that the following two conditions hold. The first condition ensures that the residual generator accurately captures the dynamics of the process given by 1. And the second condition ensures that the residual generator tracks the zero output in the absence of faults or disturbances, which is what is desired from the functional observer condition. If the previous two equations are satisfied, then the error dynamics is as shown. And if matrix A is Hurwitz, then from the zero input response, that is when the faults and disturbances are equal to 0, we can see that R of t, that is the residual, decays to 0 as t goes to infinity, which is what is desired from the functional observer condition. In this slide, we'll provide a mathematical formulation for the disturbance decoupling condition. So consider the aerodynamics that we saw in the previous slide. Our goal is to ensure that the residual R is unaffected by W, and this is only possible if the coefficients of W in the dynamics and in the output equation are equal to 0. And finally, for fault detectability, we want F to somehow affect the residual. And from the aerodynamics, it's evident that if equation 8 holds, then the fault detectability condition will be satisfied. In this slide, necessary and sufficient conditions for the residual generator to satisfy the mathematical equations for the functional observer conditions are provided in the form of a proposition. There exists a residual generator of the form 2 satisfying the functional observer design conditions 4 and 5 if and only if there exist constant row vectors v0, v1 all the way to vs that satisfy equation 9, where LF here denotes the Lie derivative operator and S denotes the order of the residual generator. If we are able to find constant row vectors that satisfy proposition 1, then the matrices of the residual generator can be designed using equation 10. Furthermore, the transformation matrix that satisfies the mathematical equations representing the functional observer conditions is given by equation 11. It is to be noted that the conditions of proposition 1 do not depend on the eigenvalues of matrix A that is given by the alphas. Therefore, the eigenvalues of the residual generator can be freely assigned to ensure rapid decay of the aerodynamics. Now we'll look at a proposition for the disturbance decoupling condition. But before that, I would like to reiterate that for the disturbance decoupling condition to hold, we would like the residual generator given by 2 to satisfy conditions 6 and 7. And it is also to be noted that A, B, C, and D satisfy the functional observer conditions, and hence they are given by equation 10. The following proposition provides necessary and sufficient conditions for the residual generator to meet the disturbance decoupling conditions. Suppose there exist constant row vectors v0 to vs that satisfy equation 9, and the residual generator matrices A, B, C, D have been chosen according to 10, so that the functional observer conditions hold with T of x given by 11. The residual generator will satisfy the disturbance decoupling conditions 6 and 7 if and only if equation 12 holds. In this slide, we present the proposition for the fault detectability condition. Before moving on to that, I would just like to reiterate that for fault detectability, we want the residual generator, the linear residual generator given by 2 to satisfy equation 8. So here's the proposition. Suppose there exist constant row vectors v0 to vs that satisfy 9, which is basically the proposition 1, and the residual generator matrices A, B, C, D have been chosen according to 10 so that the functional observer conditions hold with the transformation matrix given by 11. Then the residual generator will satisfy the fault detectability condition, that is equation 8, if and only if equation 13 holds. So this is in terms of the V vectors. We'll now see how the conditions for the residual generator derived for nonlinear systems translate to the special case of linear systems. So consider the following linear system where F, G, E, H, J, and K are now constant matrices. Now for this system, our residual generator conditions become algebraic equations, and they include again the fault detectability, um, disturbance decoupling, and also the functional observer conditions. These conditions are quite standard in fault detection literature for linear systems. The results of proposition 1, 2, and 3, which represent the functional observer, disturbance decoupling, and fault detectability conditions respectively, can be written compactly as shown in equation 14. And equation 14 is actually quite a standard equation in linear systems fault diagnosis, and it has been there for about 2 or 3 decades now. And so the results of our presentation provide a direct generalization of well-known linear system methods in fault diagnosis to nonlinear systems. Moreover, the disturbance decoupled fault detection problem can easily be extended to fault isolation, where you have a bank of residual generators, and for each fault, uh, all the other faults present in the system, all the other possible faults present in the system could be considered as disturbances. We'll now apply the results derived to a CSTR example, and here are the equations for a standard CSTR where we have some uncertainties in the reaction rates, and two faults are considered. One is a fault in the concentration sensor, and another one is a fault in the inlet coolant temperature. So we'll build two residual generators, one dedicated to each fault, and in this slide a residual generator will be built for the detection of the sensor fault F1, while F2 will be considered as an additional disturbance. So a scalar residual generator is designed, and the following two row vectors, constant row vectors V0 and V1, satisfy the conditions of proposition 1, 2, and 3. And the design parameters are as shown. They are given by equation 10 in the presentation, and the final residual generator is as shown. And in the next slide, we will consider a residual generator for the detection of cooling jacket fault F2, while F1 is an additional disturbance. And again, a scalar residual generator is built, and the constant row vectors that satisfy the propositions are as shown. And also the design parameters are again given by equation 10. You have them here. And finally, the residual generator itself is as shown. The parameters used for the simulations are shown in this table. The two residual generators are tested on the following scenario. Fault F1 has a value 0.1 and it's assumed to occur at 1 hour. Fault F2 has a value 10 and it's assumed to occur at 2 hours. W of t, the uncertainty in the reaction rate, is assumed to be plus or minus 5% of the pre-exponential factor. And the initial conditions for the simulations are as shown. So the plot of the residuals versus time is shown in this figure. Uh, from 0 to 1 hour, there is no deviation in both the residuals. At 1 hour, there's a deviation in the first residual that is dedicated to fault F1, which occurs then, but there's no deviation in residual 2. And at time t equal to 2 hours, there's a deviation in both the residuals. And so we are essentially able to detect and also isolate the faults present in the system. Coming to the conclusions, an observer-based fault detection and isolation scheme was presented. Necessary and sufficient conditions for the existence of linear residual generators for fault detection and isolation in nonlinear systems were derived. A simple design rule for the design of such residual generators was also provided. And the results were a direct generalization of well-known linear system fault diagnosis schemes that are present in literature. Thank you. And any questions?